Alright, that is actually the number one question everyone has. So I'll work out a similar example. You should always come to class with notes out before the bell rings. Suppose we had H2O molecules in a gas state moving around at 200 meters per second. If we replaced all the O2 molecule or all the H2 molecules with O2 and maintained constant temperature, how fast will the O2 molecules be moving at? So again, number one thing is temperature is equal to average kinetic energy. The average kinetic energy of all the molecules in the gas. That's the key insight. Kinetic energy is equal to 1/2 times the mass times velocity squared. So what is the mass? What is the mass of an H2 molecule? Using the periodic table, it's roughly somewhere around, so I'm going to do approximately equal to 18 AMUs. What about the mass of an O2 molecule? Well, oxygen, if you remember, is like 15.9994. So O2 would be 31.9988 AMUs. But since I'm working this out as an example, I'm going to round it and say it's approximately equal to 32 AMUs. We know that the velocity of an H2 molecule is equal to 200 meters per second. So the kinetic energy of the molecule is equal to 1/2 times the mass of a single water molecule times its velocity squared. We don't know the velocity of the O2 molecules, but we know that the kinetic energy has to be equal to the kinetic energy of the water. So the kinetic energy, well, we know the kinetic energy of them will be 1/2 mass of an O2 molecule times the velocity of an O2 molecule squared. Constant temperature means that the temperature on this side is equal to the temperature of that side. And temperature is just average kinetic energy, so that means these two must be equal, yes. We're at meters per second. So these two, if this is at the same temperature as that, and that's the same temperature as that, that means the average kinetic energy must be equal. That means we can set these two things equal. So 1/2 times mass of a water molecule times the velocity of a water molecule squared has to equal 1/2 times the mass of an O2 molecule times the velocity of an O2 molecule squared. We have 1/2 on both sides. So that means we can get rid of it, multiply both sides by 2. And so we're given the mass of an H2 molecule times the velocity of an H2 molecule squared has the equal mass of an oxygen molecule times the velocity of an oxygen squared. So divide both sides. Again, we're trying to solve for this. So divide both sides by the mass of oxygen. That cancels out on this side. And then we have mass H2O times velocity H2O squared divided by MO2 equal to velocity squared. To get rid of this square, we take the square root. Again, just algebra. So the square root of a square cancels out the square root. And so the velocity of an O2 molecule is equal to the square root of the mass of water times the velocity of water squared divided by the mass of O2. So looking it up, that would be 18 AMUs approximately. Again, this is just approximate. Times its speed, 200 meters per second squared, divided by 32 AMUs, and then the square root of everything on top. AMUs cancel each other out. 18 times 200 squared. 200 squared is 40,000. 18 times 40,000 divided by 32 gives us the square root of 22,500 meters squared per second squared. So we square the units. And then that, taking the square root of that, is equal to 150 meters per second. So because the oxygen molecule O2 has more mass, it's going to slow down to maintain the same average kinetic energy. So the O2 molecules will be moving slower because they have more mass than water molecules at the same temperature. And this is due to the fact that they have the same kinetic energy, and when mass goes up, the velocity has to go down another. I was very surprised myself that I ended up choosing random examples to get a perfect 150. Also, the reason why I used approximate numbers. You guys, though, would need to do the 18.01 something, and you would actually use the full value. But again, the whole thing was recognizing temperature is just average kinetic energy. So it's the average kinetic energy per single molecule. So that means that if we assume that all of the molecules are identical, all are moving at the exact same speed, all we have to do is find the kinetic energy of one molecule and set the kinetic energy of the other. If we assume that on average, every water molecule is moving at this speed, then on average, everyone's moving at O2 molecule is moving at that. From there, it is just algebra. Again, this class I teach chemistry and not algebra. So I assume that you know how to do basic algebra. Yeah. Equal what? Volume. That's velocity. So, technically, I made a somewhat mistake here. The mistake is I made the V too big. V is for velocity. V is for volume. Capital V is for volume. Lowercase. Yeah. So, I technically no, I kept it right. So I've been using lowercase V's. I mean, right here, this V is too big, because I was being lazy. But capital V is for volume. Lowercase V is for velocity, which is really hard to tell the difference between lowercase and capital velocity. Yes. Yes. So in your equation, it's 1/2 times mass times velocity, or your speed. Yes. That's a again, number 6 says basically it's the exact same thing. At a certain temperature, molecules of methane have an average velocity of blah. What is the average velocity of carbon dioxide molecules at the same temperature? So there, they just replaced H2O with CH4, and O2 would be carbon dioxide, which is CO2. So you do the same thing. It's just that they use 2 different elements and a different speed. I will say, I think I've mentioned this before. Make sure that if I'm using a capital or lowercase letter, you do not ever change it up. So here, I tried, I kind of was very messy. Here, I was trying, if we look, this is clearly a lowercase v, like lowercase m, because they're the same size. If I instead wanted to use capital, I would have done something like that. This would be mass times volume. T is for time. T is for temperature. We don't really use too many Greek letters in chemistry, but we will often run out of letters to use. We'll run out of the Latin alphabet, and we'll have to start using Greek letters. So every letter is corresponding to a special meaning. We occasionally will reuse some, and I'll have dual meaning, but often they do mean different things. For example, M is for mass, and capital M is for molarity. D is for distance. Capital D is for density. Again, lots and lots of meanings. So let's do an example. A closed cylinder, or I should say, let me reword this. Sorry. A 2-liter bottle containing just air is closed and closed at 70 degrees Fahrenheit. It is put in a car overnight. In the morning, you notice the volume of the bottle to only be 1 liter. What temperature is it in the morning? So a 2 liter bottle containing just air is closed at 70 degrees Fahrenheit. It is put into a car overnight. In the morning, you notice the volume of the bottle to be only 1 liter. So as temperature drops, the volume goes down. So that color, your guess is good, but your problem is you're using Fahrenheit. We don't use Fahrenheit in this class. So you're right, the volume decreased by 2. The temperature must decrease by 2. Yes. So your intuition is good, it's just that you were using the wrong units. Temperature in this class is always in Kelvin, unless we're looking at change in temperature, in which case you can use Kelvin or Celsius. So our initial temperature is 70 degrees Fahrenheit. We can convert this into Celsius by doing 70 degrees Fahrenheit minus 32 degrees Fahrenheit. Technically, you leave the numbers off. This is improper math. And multiply it by 5 ninths. Or you can put 5 ninths in front and do it. And that'll get you a temperature of 21.1111 degrees Celsius. So to convert between Fahrenheit and Celsius, so you minus 32 and multiply it by 5 ninths. Or take 5 ninths, wherever order, doesn't matter. But you have to subtract the 32 first. Then to go from degrees Celsius to Kelvin, we're going to add 273.15. And that gives us 294.2611 Kelvin. So this is the temperature we'll use. And your intuition was right, it would just be half. But let's do it algebraically first. So our final volume is 1 liter, and we're looking for final temperature. So we start with the combined gas law, PV over T equal to PV over T. Initials on the first, finals on the right. So this problem doesn't deal with pressure, so we'll assume that pressure stays constant. So we're left with V1 over T1 is equal to V2 over T2. And you are solving for T2. What is your first step in algebra to solve for T2? So what would you do in algebra? Yes. So if your x or wherever you're looking for is in the denominator, the first thing you have to do is get it to the numerator. So multiply both sides by T2. T2 divided by, so here we have a divide by. Cancel this out on this side. So we got T2 times V1 over T1 is equal to V2. Again, we're solving for T2. So there are 2 ways you can do this algebraically. I'll make a simple example over here using x and y. So let's say that we have 1/2 y equals x. We have something multiplied by y and is equal to x, and let's say we're trying to solve for y. So we can divide both sides by 1/2, and we end up with y equals x over a half. That's really the same thing as y is equal to 1 over a half times x. And how many times does a half go into 1? So that's equal to 2 times x. I prefer where we multiply by the reciprocal. That's how I do my algebra. So if we have 2y equal to x, I'd multiply by the reciprocal of the fraction, 2 over 1, multiply by 2 over 1. So I'm multiplying y by 1, so I divide it on the right side by 1. I'm dividing y by 2, so I'd multiply 2. On that side, are the 2's cancel out here, the 1's cancel out here, and we're left with y is equal to 2x. 2 over 1 is just 2x. So I personally like multiplying by the reciprocal. So 2, 1 is on the bottom, so I put 2, 1 on the top as the reciprocal, and b1 on the bottom. So now we have t1 and t1, they cancel out, b1 and b1 cancel out, and we're left with t2 is equal to v2 times t1 over v1. And you can group the v2 and t1 into a single numerator. So v2 was 1 liter. Temperature 1 was 294.2611 Kelvin. Divided by 2 liters. Liters are going to cancel each other out, giving us this Kelvin. So it's just 1/2 the temperature, which is 147.13055 Kelvin. And to get it back into Fahrenheit, we can subtract 273.15 Kelvin, or just subtract that number. That gives us negative 126.01945 degrees Celsius. And if we wanted to go into Fahrenheit, it'd be 9/5 times negative 126.01945. And then we add the 32 degrees Fahrenheit. And that tells us our temperature was 194.83501 degrees Fahrenheit. So if you had a 2-liter bottle in your Coke, you sealed it up at 70 degrees Fahrenheit, and you walk out and see that half this volume has gone away, your problem probably isn't going to be really the fact that the volume is shrunk. You're probably, have you ever seen The Day After Tomorrow? Where they showed like this hurricane or a storm comes and freezes everything. Temperature drops by 200 degrees Fahrenheit, and it starts freezing gasoline in the helicopter, causing it to crash. So you're in a Day After Tomorrow scenario if this happens to you. half a mole of helium gas is put in a 5-liter steel container. The pressure of the gas is at 31.51628855694 degrees Celsius. So the pressure of the gas, it should be at that temperature, is 2.5 atmospheres. So the pressure of a gas at 31.5 degrees Celsius is 2.5 atmospheres. If 0.1 mole of gas is allowed to escape, and the temperature drops to 20 degrees Celsius, what is the pressure of the gas? So this is dealing with moles and or relationship with moles, pressure, volume, and temperature. It uses the ideal gas law. Pressure times volume is equal to number of moles times gas constant times temperature. So when you write it in this form, these values can either correspond to all the initial values or all the final values. Here I'm going to let them be all the final values. Note that most of this entire problem does not concern itself, or does not require. Most of this problem contains useless information. What is the final pressure? Well, that's what we're trying to solve for. What is the final volume? We assume a steel container is going to maintain its shape and it's not going to shrink down. So, final volume is still going to stay at 5 liters. What is the final number of moles? Well, it started with half a mole and it lost 0.1 moles. So the final number of moles is 0.4 mole. Yeah, that's what I used. Huh? N stands for number of moles. The 2 represents that this is the final. Yeah, the N is the variable, like P is for pressure. N stands for number of moles. T, or final temperature, is 20 degrees Celsius, which is equal to 293.15 Kelvin. Looking up at our fancy chart, for in atmospheres, we would use 0.082057 liter atmosphere per Kelvin mole. So we're solving for final pressure. Final pressure would just be final number of moles times the R constant times final temperature over volume temperature. Really, you don't have to keep these 2's in it. But it's a good idea to actually make sure that we know that this equation only works at one point in time. The previous equation that we used was relating 2 points in time, initial and final. This one only deals with at one point in time. So plugging this in, final moles is 0.4 mole. Our constant might be more precise than what y'all have on yours. Table. The temperature is 293.15 Kelvin. Volume is 5 liters. And then when you write out your equation, it's good to check for units. So we have something times a mole. This mole and this mole will cancel out. This Kelvin and that Kelvin will cancel out. And this liter and that liter will cancel out, leaving us which is atmospheres. So plugging that into the calculator, we get 1.9244 atmospheres. So the pressure inside went from 2.5 atmospheres to 1.942441 atmospheres. That corresponds to a 23% drop in pressure, but we lost 20% of the gas. By the way, if you ever see this notation, so usually the units for R, if they use atmospheres, you'll see they correspond to something like liters times atmospheres times Kelvin to the -1 times mole to the -1. What does this -1 mean? If I took X and raised it to the -1, what does this equal to? Have y'all been taught exponents? This is 1 over X. X to the -2 is just 1 over X squared. So this negative means it's going to be just dividing by whatever the number is. If it's -1, it just means divide by K. So if it's X to the -1, it just means 1 divided by X. So I've written it here, L times ATM divided by K times mole. Sometimes you'll see it written like this. They're the same thing. X to the 1/2, I'll make it negative. So the negative means that this is equal to 1 divided by X to the 1/2. And what does X to the 1/2 equal to? The square root of X. So X to the 1/3 is the cubic root of X. Suppose you have an empty 500 milliliter bottle. That's their normal water bottle that you have on your desk right now. They're 500 milliliters. And your vehicle. And you closed it. You closed it at 77 degrees Fahrenheit, which is 298.15 Kelvin. During the night, we had looked this up during 4 period, it should get down to 66 tonight. During the night, it cools to 66 degrees Fahrenheit, which is 292.039 Kelvin. What is the volume of gas inside the bottle at night? So again, initial volume is 500 milliliters. Initial temperature, we use Kelvin, so I'll take those values. Final volume is what we're looking for. Final temperature is 292.039 Kelvin. So, combine gas law, initial pressure times initial volume divided by initial temperature has to be equal, has to stay constant, so it doesn't change. This ratio doesn't change, so it has to be equal to the final versions. We don't care about pressure, we assume it's constant. So V1 divided by T1 is equal to V2 over T2. So we're solving for V2. This being divided by T2 on the bottom. So to move it over, we'd multiply by T2. So that cancels out. And so V2 is equal to T2 times V1 over T1. Plugging that in, 292.039 Kelvin times a volume of 500 milliliters divided by a temperature of 298.15 Kelvin. Kelvins cancel out. We're left with milliliters. So plugging that into the calculator, we get 489.7518. So a loss of 11 degrees Fahrenheit, going from 77 degrees Fahrenheit to 66 degrees Fahrenheit, we end up losing a little over 10 milliliters of volume. Probably wouldn't notice it occur when you get stepped into your vehicle in the morning, as a small volume compared to the volume of the bottle. You might have noticed in winter though something else occurs. Like you can see your bottle really crushed. Does anyone know why this happens more in winter? First, we get a bigger temperature change. It's not just around 10. We can go from it being in the 60s down to it to be in the 30s. So you can see like 30 or 40 degree temperature changes. So we can see it go significantly more than this during the winter. Another thing is the amount of water vapor that can be absorbed in air is dependent on temperature. So as something cools down, so if you didn't have pure water, if you didn't have pure air, so we have a water bottle and it has some H2 molecules floating around inside of it in the gas form. So H2 has vapor. What can happen is when your temperature drops, it'll form bubbles around the side on it and turn from a vapor into a liquid as temperature drops. with a little bit of gas still floating around, just not as much. Now, gases take up a whole lot bigger volume than liquids do, so the volume of the gas will significantly drop compared to. During winter is a combination of the vapor going into the liquid and the gas losing volume due to temperature change. That's it for today. Here's the code word. So finish up your homework. I think the only challenging one will be the last one. I think the only challenging ones will be the last one. I might just do that as bonus or something. No, the gas ball one.